Hello everyone, welcome to the Statistical Foundation for Big Data Analysis. Today we will start module 2 which will be the first module on statistical inference, and today we will discuss the sort of the basic framework of point estimation, and we will talk a little bit about one key feature, key important topic, unbiased estimation. So, let us start with this little flow chart. Remember, we discussed that statistics is all about deciding about a population, the sort of all measurement of certain kind based on a sample collected out of it. Now, inference is of two types. We will see the inference is of two types: estimation and testing or hypothesis testing. In case of estimation, what we try to do, we try to predict some value, guess some value, make some educated guess, predict some value associated to the distribution of the population. The simplest example was this coin tossing example, where you are trying to guess the head probability. You had a coin, you were trying to, based on 100 tosses or 10 tosses of that coin, you are trying to guess the inherent head probability. I use the word inherent to remind, like we were discussing that whether there is something inherent or not, and inherently there is some head probability to a coin or not, and we sort of said there is something like which one can say this is inherently the head probability, and there is some asymptotic rationale behind it. But there is another type of thing you can do regarding a population, another type of inference you can do, where instead of trying to predict a particular value, what you can try to do, you can compare two statements. This is quite important, and this plays a very vital role in statistics. What kind of statement? So, let us see. So, what you can do is that, like, some simplest thing will be, you can try to guess that given two values, which one is better, which one is better suited. So, you want to compare two values, you can compare two statements. Okay, this is all vague. So, let me just give you an example. Again, back to the coin tossing example. You have a coin with certain head probability which is sort of unknown. Based on n toss, you try to compare the two predictions about the coin, one head probability half, another head probability 0.9. You want to compare which one is more likely. Now, obviously, if you have tossed a coin and you got a tail, if you are comparing between, and you want to predict using just one toss, based on this result, this outcome, tail, if you have tossed a coin and got a tail, if you want to predict which one is more likely, whether head probability half and head probability 0.9, an educated guess will be head probability half is more likely, because although half says there is reasonable probability of getting head, but the fact that you have got tail, it seems like 0.9 is a far more unlikely case, because if you have 0.9 head probability, if you have tossed a coin, it is far more likely to get a head than, let us say, when the head probability is half. The fact that you have gotten tail, if you have to choose between 0.9 and half, you probably will choose half. But the point is that, like, things are not always this neutral. In case of comparing two statements, we will see when we are going to do hypothesis testing in details. In today's talk, by the way, we will mostly concentrate on estimation, not only estimation, a special kind of estimation, point estimation, but just I couldn't resist giving you a glimpse. More often when we are doing in hypothesis testing scenario, the two statements you are comparing about a population, they are not symmetric. So, now just to give you a real life example, even if it is a bit morbid example, suppose a patient has come to an oncologist. Now, the oncologist faces a choice, patient has certain symptoms. The oncologist faces a choice whether the oncologist detects in his primary detection, whether the oncologist detects the person has cancer or malignancy, or oncologist detects the person does not have cancer or malignancy. It is a primary guess, primary prediction, primary analysis. The oncologist has to choose between these two scenarios. His first initial guess is that a patient has cancer or patient does not have cancer. These two statements leads to potentially each of them can lead to two different errors. The first one, if the oncologist predicts a patient has cancer, the error affiliated to that is, well, he has predicted cancer when the patient does not have cancer. The second one, the oncologist predicts the patient does not have cancer, leads to a situation where the patient has cancer and the cancer does not get detected. Now, which error is more serious? We cannot say these two are symmetric situation. Even if the patient gets detected by the oncologist, like wrongly gets detected, by oncologist to have cancer, there will be of course series of tests that will follow. And if the patient does not have cancer, it will get detected. Although the patient will get temporary scare, this is far less serious than if the oncologist tells the patient that he does not have cancer and the cancer does not get detected, and then eventually it gets caught in maybe third or final stage when there is nothing to do. And this is sort of the situation are extremely prevalent and covered by this hypothesis testing theoretical framework. Two statements which are not symmetric. Another business example, suppose in India, paracetamol is one of the most common fever medication, crocin, Calpol, all these things. If a new company is bringing a new drug for fever, and wants to do a market survey or wants to do a, let us say, a clinical trial where they want to guess whether they are a clinical trial for guessing whether this is a good business venture or not, what will the company do? The company will test on a bunch of people the new medication and see its performance compared to the performance of paracetamol. Now, here also this is also another situation where the two scenarios affiliated to this are not symmetric. The first one, the paracetamol performs, the crocin or Calpol or the existing paracetamol does better than the new medication. Another is the new medication does better than the paracetamol. The point is this: to launch a new medication in market, the company has to invest a lot in marketing. Of course, actually, generating the medication, that cost is there, but also there is marketing and everything. But the point is, if the medication just barely does better than the paracetamol, that is not a good business venture, because paracetamol has this amongst the people's mind of people, there is this inertia. Whenever there is fever, you get paracetamol, you have Calpol 650. The new medication, it is not enough for the new medication to be just better, it has to be overwhelmingly better to defeat the market reputation of the existing medication. So, this is where what becomes very common in hypothesis testing. One hypothesis often is the status quo, or let us say the standard wisdom, this is what you should do, and the other one is the alternate, which has to outperform it a lot to become the new status quo, or let us say outperform it a lot to find a place for its own. So, we will get into details about this, but now it is an estimation. So, in this talk and this first week of statistical inference, we will discuss estimation or the point estimation and interval estimation. So, here basically the goal is, based on the sample, we want to predict some value associated to the population. So, this is the setup. You have sample, so your population is represented by random variable x with distribution. Now that we saw some random variable notation and distribution notation, often we denote the distribution by this cumulative distribution function. So, this is the CDF of f, the cumulative distribution function, simply because probability mass function, that is probability assigned to individual values, that comes in case of discrete, and the probability density function, this function whose integral gives you probability, which is associated to absolutely continuous. I mean, like, they are very case specific, but for every case you definitely, for any kind of probability, you always, any kind of random variable, you always have this CDF. This is always the case. I mean, every random variable has this function. So, it is often common to denote distribution by this CDF. So, you have population which follows this distribution, and your sample is x1, x2, xn. Each xi, for all I, xi also has the same distribution as x, because after all the samples are being drawn from the same population only. So, the uncertainty or the randomness affiliated to the population will be same for each sample. So, this is what is written here, and now basically what we try to do, we try to predict a value affiliated to the population based on some function of the sample. These functions are called statistic, sample statistic. Based on the sample statistics, we try to predict a value affiliated to the population. So, this is one example. I mean, we have seen all these examples before. Still, just to hammer it more, predict the head probability of a coin using the number of heads in n tosses. We saw that one guess is that the proportion of heads. If suppose the population is normal distribution, remember we discussed normal distribution in mu sigma square, which follows this kind of bell curve. Predict the center of the population, or the population average, the expected value of the population, this mu, based on the mean of the drawn sample. We will see today itself that this sample mean for normal distribution is actually a kind of a good predictor for the population mean. Another kind of approach in point estimation is to try to predict an interval within the, so predict an interval, sorry, this variance is a typo, I will get it corrected in the notes. So, this predict an interval for the variance of the normal distribution, that is, you want to predict this sigma square, you want to predict this sigma square based on a sample x1, x2, xn. One guess is that you just simply take the sample variation. Suppose you have a normal population, you want to predict normal mu sigma square, you want to predict the variability of the normal distribution. Now, to predict the variability based on the sample, well, one guess is, of course, if the sample is representative, if the if the population kind of shows this pattern that most of the things are clustered around this, and then suddenly it is kind of getting spread, the population variation is, one may expect, is reflected in this sample variation, the classical variance of bunch of points. And this is one approach, that you want to predict an interval like a b using this, like both a is a function, basically function f1 of this sample variation, summation xi minus x bar whole square. This is a function, and b is also another function of the same thing. We want to, this is another approach where you want, what you want to do is you want to predict an interval such that it is highly likely that sigma squared falls inside this interval. Now, we will get into the details of interval estimation as well as hypothesis testing in the second week of inference, when we do statistical inference too, and we will see that they have very interesting connections, this interval estimation and hypothesis testing. For now, we will remain in the domain of estimating a particular point affiliated to a distribution. So, now we are in a position to talk about the classification of estimation itself. Just like inference, statistical inference has this two types of things going on, point estimation and testing. Estimation itself can be classified into two groups, point estimation and interval estimation. In last page we saw these two examples where these three examples where the first three, sorry for this disturbance here, the first three where you are trying to predict the probability of a coin using n tosses, just the head probability or the center of the normal distribution, those were point estimation because you are trying to predict a particular value, and the last one where you are trying to predict an interval for the variation, that is called an interval estimation. The next what we do is we just basically tell you what the basic framework of hypothesis testing. We already discussed this. It tries to decide between two given options about the population, which one is more likely. Just a quick example, based on results of n tosses, try to decide between two values p1 and p2, which one is more likely. I already gave this example where you toss a coin, here let us take n equal to 1, toss a coin where you got tail. Based on that, try to predict whether it is more likely that head probability is half or head probability is 0.9. Another is based on sample from normal distribution, try to decide between two variabilities which one is more likely. We will get into the nuances of hypothesis testing when we do it, just as an example. Before we move on, I wanted to recall something from basic probability, namely independence. So, probability of two sets, so two sets A and B are called independent if probability of A intersection B is just the product of the probabilities. Bunch of random variables x1, x2, xn are called independent if basically when you are trying to consider probabilities, simultaneous probabilities of each of them belonging to certain sets. For any set, that's actually becomes, sorry, this is a typo. So, this becomes a probability of x simultaneously xi belong to ai becomes just the probability of the product. So, it becomes the product of the probabilities. So, probability of x1 belong to a1 dot 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 xn belongs to an is nothing but product of the probabilities xi belong to ai for I running from 1 to n. Unless otherwise, and this is true for all. So, you need this for all a1 to an, any collection of sets you want this. So, basically random variables are independent if and only if the corresponding, you just pick any sets affiliated to those random variables, they together are independent. Now, unless otherwise stated, the sample, the random variables representing samples drawn out of population are independent for this course. So, what we call independent and identically distributed sample. So, basically what happens is that like so this word random sampling that we will keep using in data science, it means basically you have the population ambit of all measurement, you do one measurement, keep the record, simply forget it, do another measurement. Now, this can be multidimensional, by the way. What can happen that n experiments together may form one measurement. In that case, the population will be all collections of n simultaneous experiments of, let us say, a particular experiment. That is also possible, but the point is one shot you do it, record it, kind of forget it, do it once more. So, you want this because you want it to be a representative. So, basically what you, just to talk in terms of an example, when you are doing coin tossing, you toss the coin, record it head or tail, and then toss it again, forgetting what happened in the previous toss. The previous toss does not affect next toss. Similarly, for when you are working on this height versus weight problem for Indian people, when you are drawing a sample, randomly select one person, draw height and weight, forget that person, select another person from the whole population. I mean, very unlikely you will end up selecting one person, but the point is this becomes really important to make sure each of them are being drawn from same population. So, if you are drawing something and discarding it, this may influence the probability structure in the population, and you have to take into account. So, your concern is that to predict about the population, you want the n iteration of the same experiment. So, once you have done an experiment, you want to make sure next time you are doing the same experiment only, the results of this experiment on the act of doing this experiment has not altered the population, because if it has altered the population, you are inferring about this different population out from the next experiment you are drawing. So, this is something is extremely important, and this when we do sampling, we ensure that all these random variables are coming out of same population only, independently of each other. They are not, result of this is not, result of one experiment does not affect the other one. So, basically for sample x1, x2, xn for a population with CDF fx, for some random variable x, we have x1, x2, xn that are independent and identically distributed. The notation for that is IID. You will keep seeing this in statistics with CDF fx. Sorry for being nagging about this point a bit, but this is actually important. So, now we can go into point estimation. So, in this course we will cover some of the basics of point estimation. We will talk about unbiasedness, and this notion of bias will come later when we will do certain more advanced topics in this course. We will discuss likelihood and maximum likelihood estimation. We will discuss method of moment estimation and certain asymptotic behavior of the point estimators. These are the topics we will do. So, unbiasedness, let us discuss unbiasedness, and before we move on to some examples of it, we will also discuss some basic facts from random variables. So, suppose theta is a value related to the population, and suppose t is a function of the sample, that is t is a function of x1, x2, xn, the sample drawn out of the population. T will be called an estimator or a predictor of theta if this is an educated guess for theta, like a portion of heads in n tosses, we were guessing that that is a good, we were guessing that as a representative or a predictor for the actual head probability, had certain intuitive understanding of it, or average of a population of a sample. The sample mean is a sort of a good guess for the population mean, under the assumption is the sample is kind of representative. So, some intuitive, not necessarily rigorous mathematical, but some intuitive rationale behind this is something we demand. Frankly speaking, we can make it even more rigorous and say any function is a predictor for theta, as bizarrely unrelated it may be, and then say that we can define a loss function and say that this is very bad or this is somewhat good. That is formality we can do, but generally speaking, for real life application, when we are trying to predict something, we start with certain intuitive understanding, like say that this may be a good predictor. So, that is why I have kept this educated guess within bracket. Before we move on, this example which we kept repeating, like portion of head being a guess for head probability or sample mean being predictor for population mean, this is basically coming from this notion of unbiasedness, these intuitions in some ways. A predictor of a value theta associated to population using sample x1, x2, xn is called unbiased. Now, we are in a position to talk about define it. If expected value of theta is t. Now, t is a function of bunch of random variables. So, t is a random variable. So, whatever the distribution, whether we can calculate it or not, that is a separate thing, but x1, x2, xn are random variables. So, it is the coming from the same distribution as the population. So, values of that is, these things are probabilistic. So, the values of t is also sort of probabilistic. So, it makes sense to talk about distribution of t and the expected value of t. So, if expected value of t is theta, then it is called unbiased. Now, whether we can actually say this is actually unbiased or not, whether you can find and prove this is expected value is t or not, that is a separate thing. I mean, whether we can find it or not, that is a separate thing, but it is called unbiased somehow if we know that expected value is theta. So, some facts about expected value: if z1, z2, zn are random variables, expected value of the sum is the sum of the expected value. So, this is essentially if you have a bunch of few groups of numbers, average of the whole things are sort of can be calculated from average of each of the group. If they are same, they are just sum of the averages. It is roughly that. I mean, you can calculate basically average of bunch of groups from averages of each of them. You have to properly normalize. It is not exactly sum, but like you have to take the weights carefully. So, that is the notion behind it, and expected value of some constant times some random variable is just the constant times the expected value of the random variable. And if you have pairwise independent random variable, if a bunch of random variables are independent, then if you take the variance of some constant times these random variables and then take sum, this becomes the variance. You just sums this squares of the constants comes out, and those squares times variances you do and take the sum. That is the formula for having variance for these sort of constant times zi's and their sum. These formulas are quite important for many of the calculations. So, this theme of sample mean being unbiased estimator or nice estimator of population mean is actually a recurrent thing in statistics. You will keep seeing that this will keep repeating itself in various contexts. Just to give you an idea, so there is nothing really specific about finite population. If you take x1, x2, xn independent and identically distributed Bernoulli random variables, recall that that we mentioned that IID means independent and identically distributed, that is x1, x2, xn are independent random variable, that is the underlying sets are independent, and they are also all of them have same distribution, namely Bernoulli p distribution, that is each of them takes value 1 with probability p, value 0 with probability 1 minus p. In this case, if you take the mean of x1, x2, xn, that is summation 1 over n summation 1 over n summation I running from 1 to n xi, the expected value of this thing is actually p. So, it is pretty easy to see because expected value, as we mentioned earlier, the constant terms comes out of the summation, constant terms comes out of the expected value, and expected value distributes over sum. So, basically when you have, recall, expected value of x1, or rather let me use a slightly different notation, recall that we discussed expected value of z1 plus zn is same as summation expected value of zi, hence expected value of, and also expected value of some constant times z is constant times expected value of z. Now, if you take this summation, this we saw this in the previous example also, but just for the sake of completion I am just writing it again just to hammer the point. If you have 1 over n summation xi. Now, this 1 over n is a constant, this summation is a total entity on its own. So, this is like this z here. So, 1 over n comes out, you have expected value of this summation xi, but then summation xi is just the sum xn. Now, compare with the numerator, this just becomes 1 over n expected value of x1 expected value of xn. Now the point is each xi is Bernoulli p. So for all xi, expected value of xi is nothing but 1 times p plus 0 times 1 minus p. Recall that if you have a random variable x taking values x such that probability x equal to ai is pi, the expected value is sort of the distribution version of weighted mean. Expected value of x is nothing but summation ai times pi. This is what is being used here. So this expected value is just nothing but summation 1 over n and sum of n many p's, so that gives you p again. But the same thing, I mean, if you see this is sort of distribution free actually. You will realize in a moment. Instead of Bernoulli, if you take normal mu sigma square, the same phenomenon repeats. You take x1, x2, xn IID normal mu sigma square, then actually for the same x bar, that is the mean of these x1, x2, xn, we still have expected value x bar is mu. Actually, it has nothing to do with the particular distribution. In fact, if you have now, I mean, I'm writing the specific case only just to give you an idea, but just now to show you what's going on. These are IID with mean mu. If you just have a same mean, that's all. You don't even need normal or by Bernoulli anything. Then already then that's enough to give you this expected value of x bar equal to mu, because this calculation, this is just follows from the properties of expected value, that 1 over n comes out and expected value gets inside the sum, and each of them has expected value mu, so you just get n many mu's. So 1 over n times n mu, that gives you mu. So this is the phenomenon I was saying, that sample mean keeps, sample mean being a good estimator of population mean, that comes creeping in statistics everywhere. And as we saw, one example with finite population, and this is more like an abstract population. There also it's showing up. Now the situation becomes slightly interesting when instead of mean we get variance. So just to give you an example with the finite population, the same setup as the finite population case for sample mean. If you have x1, x2, xn finite population and y1, y2, y small n and IID sample, if you are looking for an unbiased estimator for the population variance, that is 1 over n summation, sorry, this is a type, sorry. So this is a typo, this should be n, my bad. So if you take the population variance 1 over capital N summation j running from 1 to n, and this is j, then sample variance in the sense like you replace 1 over n by, so 1 over small n and x's by y's, you would guess that this will be an unbiased estimator, but this doesn't become an unbiased estimator. What happens, these calculations, if you go ahead with these calculations, this is a slightly involved calculation here. What one can show that the unbiased estimator of population, so unbiased estimator for population variance is actually this 1 over n minus 1 version of sample variance. So population variance 1 over n summation j running from 1 to capital N, xj minus x bar whole square, and y's are IID sample. This is so call this population variance Vp, let's say, and let's say I'm just now using unconventional notation. So the first version, the immediate intuitive version of sample variance, the 1 over n summation yi minus y bar whole square, I running from 1 to n. This is, so expected value of V1 is not equal to Vp. However, if you take V2, where you take 1 over n minus 1 summation I running from 1 to n yi minus y bar whole square, expected value of V2 is Vp. The calculation is bit involved. I have put it in the notes. You can take a look at the calculation. So this is the calculation, and I am not getting into all the details because it sort of involves the playing with summation and certain things cancelling out each other. It's just involved a basic elementary algebra of summation symbol. That's all. This is a rather long calculation. You can take a look at it peacefully. Okay. Thank you. Let me stop here.